Chapter 9, Electrolyte Solutions, Section 9.5, Chemical Equilibrium in Electrolyte Solutions. First, let's review the activity of a solute in an aqueous solution. There are two different definitions. The activity can be the activity coefficient times the concentration in molar over C0. The activity can be the activity coefficient times a molo over M0. So C0 is 1 mole per liter solution. M0 is 1 mole per kilogram of solvent. Why do we have these two different definitions? Well, it's just because very often it's more convenient to use molar. It's easy to just measure the volume of the solution. But on the other hand, if you want a more accurate concentration, use molo. It's just because when you have 1 mole solute per kilogram solvent, the mass of the solvent never changes with the temperature. But if you use molar, you know the volume of the solution very likely changes with the temperature. When temperature goes up, very likely the volume goes up a little bit. When temperature decreases, very likely the volume of the solution also decreases. So even if you have just the same amount of solute and solvent in the same solution at a different temperature, you will get a different molar concentration and a different A. So that's very unfortunate. But still, we often use molar again because of the convenience. And anyway, for water aqueous solution, very likely if you have 1 liter aqueous solution, roughly you have 1 kilogram of the solvent water in the solution, approximately. So we have this kind of equivalence here. And therefore, for an aqueous solution, very often it's okay to use C0, it's okay to use M0, it's okay to use molar concentration or molo concentration, as long as you understand, well, if you use molar, it's just a approximate value at a given temperature. When you use molo, it's more accurate. They are about the same if water is a solvent. Now let's just use molar for convenience. In the expression of the solubility product K sub Sp, A is often expressed as the activity coefficient times molar over C0. Again, for convenience. It's mostly for convenience. And if you do that, usually we specify the temperature, very often room temperature. In KSP, SP stands for solubility product. So you can also say this is the equilibrium constant of solubility product. So usually we use this to measure the solubility or to quantify the solubility of an ionic compound. Let's look at one example. Let's look at magnesium fluoride. All right, it can decompose into magnesium cation and fluoride anion, and its solubility product can be expressed as the activity of magnesium cation times the activity of fluoride squared. Why squared? Because you have a 2 here, that's why it's squared. And now we can express A as gamma times C over C0. So we have over here, this is just gamma times C of magnesium over C0, and the activity of fluoride is gamma times C of fluoride divided by C0. And remember, when we have 1 magnesium 2 plus at the same time, we get 2 fluoride in the aqueous solution, and that's why this concentration of fluoride is actually 2 times the concentration of magnesium 2 plus. And then again, we need to use the mean ionic activity coefficient. We cannot separate cations from anions. We have to use this mean ionic activity coefficient for both ions. So we have this gamma plus minus to denote the mean ionic activity coefficient. It's raised to the power of 3 because over here you have a gamma and over here you have gamma to the power of 2. And now we have this expression. Remember to divide C by C0 always in the expression of equilibrium constant, because an equilibrium constant must be unitless. Alright, this is just the standard molar, 1 molar. And now let's look at this equation. Why do we have a 4 here? Very simple. It's just the concentration of fluorine minus is always 2 times the concentration of Mg2 plus. And also we can just denote the concentration of Mg2 plus by this concentration of MgF2 in aqueous solution. This is just a notation, so really this is just equal to the concentration of Mg2 plus. This is different from the concentration of fluoride. It's just because when you dissolve only 1 unit of MgF2, you get 2 units of F minus in water, and this has to be squared. That's why you have a 4 here. So again, we have this equation over here. We will use the method of successive approximation to calculate the solubility of this MgF2. So this value, we'll calculate this value given the solubility product of magnesium fluoride. Why do we need this successive method of successive approximation? Well, it's pretty simple. It's just because we do not know the value of gamma here. If we do know the value of gamma, we plug it in, and if we know the solubility product, we can simply solve for the concentration of MgF2 in water because there's only one variable. However, in this expression, we actually have two different quantities that we do not know their values. We do not know this gamma, we do not know this C. Why don't we know this gamma? Because we don't know the ionic strengths. Why don't we know the ionic strengths? It's just because we do not know how much magnesium cations and chloride anions are dissolved in water for that reason. Again, let's look at this example. Magnesium fluoride decomposes into magnesium cation and fluoride anion at room temperature in water. So this is going to be given to you. For example, this solubility product of equilibrium constant for this is 6.4 times 10 to the power of -9 at room temperature. Again, very likely this value will change as temperature changes. Usually this value increases as the temperature increases. How can we determine the solubility? Again, we have this equation, but unfortunately we do not know the value of gamma, and we do not know the value of C of MgF2. So this is just how much MgF2 is dissolved in water. So again, how do we solve this method? We're going to use the method. How do you solve the problem? We're going to use the method of successive approximations. First, we're going to just assume gamma is 1. Of course, that's not true because we have a ionic solution, we have a positive ionic strength, and then we have gamma less than 1 because the cations and anions stabilize each other, and also they are stabilized by surrounding water molecules. So gamma is supposed to be less than 1. But anyway, let's assume gamma is 1 to do the calculation. And now gamma is 1, we replace gamma with 1, and we can easily solve this because we know the value of KSP. It's right here. We solve this equation. We get the concentration of MgF2 is 0.00117 molar. So this is just the first step. We assumed gamma is 1 and computed the concentration of magnesium fluoride right here. However, gamma should be less than 1. Now, given this value, again, this is not the exact value, but given this value, we can actually compute the ionic strength of the solution with this concentration. We're going to assume the molo is equal to the molar because water is the solvent, and it's a fairly dilute solvent. So we're going to say 1 liter solution contains approximately 1 kilogram of water. So let's compute I is this molo over 2, and then times 1 times 2 squared plus 2 times 1 squared. This is magnesium with the charge squared. This is fluoride with the charge squared, and this 1 and 2 are the coefficients. And now we get 0.00351 molo, which is mole per kilogram of solvent. We can compute the value of gamma this way. Our gamma is negative 1.173 times the charge of magnesium, the charge of chloride, and then the square root of ionic strength. We get a small negative number, and then gamma is e to the power of negative 0.139. Gamma is 0.87. So we get a new value of gamma. It's no longer 1, and we use this new value of gamma to plug into this equation, and KSP is still this value. and now we have just a new gamma. Once we plug in the new value for gamma, we get this 0.87 cubed times 4 times this cubed. We solve this equation and we get a concentration of magnesium fluoride to be 0.00134 molar, and this number is greater than this number. Again, it's just because now we are considering the activity coefficient being less than 1, and that means we are considering this magnesium cations and chloride anions stabilize each other in water, and therefore we can dissolve more. And now we have a updated value for the concentration of this ionic compound. We're going to use this new value to compute the ionic strength again. And after we get a new value for ionic strength, we get a new value for gamma. Once we have a new value for gamma, we will set up this equation again to compute the concentration of this ionic compound again, and we keep updating the values until the last two values converge. Again, just a review. First, we assume gamma is 1, we get a concentration here, and then given this concentration, we compute the ionic strength and a updated value for gamma, which is 0.87. Using this gamma value instead of 1, we get a higher concentration of the ionic compound. Now, using this concentration, we can compute the ionic strength again, which is 0.004 molar. Using the new value of ionic strength, we can compute gamma again. This time, gamma is 0.862, slightly lower than the previous value, and then we'll be using this new value of gamma plus minus to compute the concentration of magnesium fluoride again, and we get another value 0.00136. Compare this value and this value, you can see the last two values of the concentrations are really close to each other. Now we're going to use this value 0.00136 molar magnesium fluoride in water to calculate the ionic strength again. Just by replacing this 134 with 136, we get a new ionic strength. We plug in the new value of ionic strength, we get the value of gamma again. Well, we keep doing this until the last two values of the concentration and gamma converge. And actually they do converge after one or more steps, and then gamma is actually 0.0861. The concentration of magnesium fluoride is 0.00136 molar. And we know it's converged only because in the last two iterations we have the same value. And at this point, not only the concentration is converged, the ionic strength is converged, and gamma, the activity coefficient, is converged. At room temperature, we determined the solubility of magnesium fluoride in water as 0.00136 molar. And this is definitely higher than 0.00117 when we assumed this gamma is simply 1. So yeah, you of course can first assume gamma is 1 to get the concentration, but just do not stop there. Once you have a value for concentration, you can compute the ionic strength and a new value of gamma. Once you have a new value of gamma, you can compute the new value of the concentration. You keep doing all these iterations until the values are converged.